I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss about the topic batch normalization. First, we will see the introduction to normalization. Normalization is a data processing technique used to bring different features in a data set to a common scale, which helps machine learning models converge faster and perform better. Without normalization, the features with the larger numerical ranges can dominate the learning process, causing imbalance and inefficiencies in model training. Importantly, normalization does not distort the shape or distribution of the data. Instead, it adjusts the scale to ensure all features contribute equally. This technique is crucial in both data preprocessing and within deep learning architectures where internal distributions may shift over time. Next, what is batch normalization? The batch normalization that we are calling it as BN represents batch normalization, is a technique. It is designed to improve the performance and stability of deep neural networks. It achieves this by normalizing the input to each layer so that the distribution remains consistent during training. Specifically, batch normalization standardizes the input activities. It standardize the input activations for each mini batch, meaning the normalization is applied not to individual inputs but to groups of inputs processed together. This helps reduce the problem of internal covariate shift where the distribution of activations changes due to updates in network parameters. By stabilizing these distributions, batch normalization allows deeper networks to be trained more efficiently and with greater robustness. Next, how batch normalization works. The batch normalization process works by calculating the mean value. This mean value is applied by and standard deviation of the activation functions for each hidden unit with a given mini batch. One more time I'll tell you, the batch normalization process works by calculating the mean value and the standard deviation of the activations of each hidden unit within a given mini batch. These statistics are used to perform Z normalization, that we can call it as Z normalization, which centers the data around zero and scales it to unit variance. After normalization, the result is scaled and shifted using two trainable parameters, that is yj and this gamma j, allowing the model to maintain flexibility and recover the original distribution if through activation functions like ReLU or sigmoid, ensuring that subsequent layers receive inputs that are consistently scaled and centered. Next, so this is given by the formula. Apply z nor is a z caps equal to, this is the value a z minus mj divided by sj, and the rescale and shift with the learned parameters are given by the formula yj is equal to gamma j and aj gap this value plus beta j, and with the activation functions we are using in this case is ReLU and sigmoidal functions we are using. Next, internal covariate shift, as I've said in the previous slide. Internal covariate shifts refers to the change in the distribution of inputs to hidden layers caused by continuous updates to the model parameters during training. As each mini batch of data may differ slightly, this constant shift makes it harder for the network to coverage quickly since each layer must continually adapt to new distributions. Batch normalization addresses this problem by stabilizing the inputs to each layer, thereby reducing the effort needed by each layer to adapt to changing inputs. This stabilization is especially important in deep networks where layer wise fluctuations can greatly hinder training performance. Example, if you are taking in practice, consider a deep neural network trained to classify images of dogs. Let us say, for example, we are going to train the network by making use of the images of dogs. If the training data initially consists of white dogs, the hidden layer will learn to respond to features specific to that distribution. Later, if images of non white dogs are introduced, their different pixels distributions will cause the activations in the hidden layer to shift. This shift in the hidden layer activations is a practical example of internal covariate shift. Batch normalization in this problem, what the batch normalization will do is the batch normalization helps by adjusting these activations during training so that such changes in input distribution do not destabilize the network, allowing it to learn consistently across different types of data. And what is the advantages of batch normalization? Batch normalization provides several advantages that make it a key component in model deep learning. It significantly speeds up training by reducing internal covariate shift and allowing higher learning rates without the risk of divergence. And also, BN reduces sensitivity to hyperparameters such as initial weights and learning rates, making model tuning easier. Furthermore, it smooths the loss function, improving behavior of gradient descent and helping the model find better minima. In many cases, batch normalization can also act as a regularizer, reducing need for dropout and other regularization methods and improving generalization. Next, learnable parameters in BN. A key feature of batch normalization is the introduction of two trainable parameters per hidden unit, that is gamma j and beta j. These parameters are learned through backpropagation just like weights and biases. They allow each hidden unit to learn its own optimal mean and variance, thereby preserving the network's representational power even after normalization. However, this also means that batch normalization adds some computational and memory overhead during training, which must be considered when designing large scale networks. Despite this, the benefits of batch normalization typically far outweigh these costs and limitations of batch normalization. Despite its many advantages, batch normalization has some limitations also. It does not perform well with very small mini batches or in online learning scenarios where data is processed one sample at a time. This is because BN relies on meaningful batch statistics to perform accurate normalization. Additionally, calculating the mean and the variance for every batch adds computational costs. During inference, using moving averages from training ensures consistent behavior, but careful handling is required to maintain the accuracy and of these statistics across different data distributions. and testing phase of batch normalization. During testing or inference, batch normalization does not compute the mean and variance from the test sample. Instead of it use the mini batch and standard deviation computed from training phase or raw data subsets. This ensures that consistent behavior across all test samples and prevents fluctuations caused by smaller irregular test batches. The learned scaling and shifting parameters are also applied during the inference, allowing the network to maintain its learned representations while benefiting from the stabilization offered during training. And finally, why use batch normalization? Batch normalization is essential in deep learning because it mitigates the effects of internal covariate shift, a problem that slows down learning and destabilizes training. By standardizing the input to easier each layer, BN allows networks to learn faster, converge more reliability, and generalize better. It facilitates the training of very deep models by preventing the divergence that often occur when activation distribution shift. In essence, batch normalization makes the optimization landscape smoother and more predictable, greatly enhancing the performance and usability of deep neural networks. Hope everyone understood about this batch normalization techniques, why we are going for the batch normalization techniques, and how the variants are being adjusted in the hidden layer. The remaining things we'll discuss in the next lecture. Thank you.